There we go. So here's the check-in link. I can put it back up at the end if you want. But let's get started. So we have a lot to cover today. So we have 2 meetings left, including this one. We have this one and then the one next week. So the Thursday after break, which is December 2nd, I think. Let's see. Yeah, December 2nd. And then December 9th, like that's the week of tests. So that one's going to come. So we got 2 left. Unfortunately, I sort of talked about this last time, but I had to cancel some of them because I had tests like at this exact time on Thursdays a couple of times. But I'm going to try to get through everything that we wanted to. So the goal of this, like what all these things were leading up to, is teaching you a bunch of like fundamental skills and just showing you these things. And then, yeah, I am. Yeah, I just started that. I think I did, but it didn't do the voice, did it? Yeah, it says it is. Okay. So all that was with the goal of eventually looking at some extremely complicated problem and using all those things and sort of cobbling them together to get a solution that works. And so this is that problem. So today I'm going to introduce it to you. I've decided not to do, at least for this time, I don't know how fast I'm going to be able to go on this. And so for this time, I'm not going to be showing any code. Next time, I might do that. It'll all be pre-written because we just do not have time to do that live, unfortunately, because that's like the cool part. But I will do my best to sort of explain all the code that we would write and also visualize it, because this is a very sort of graphically driven algorithm, I think. Okay, so let's get started. So the problem we have, well, I guess first I can actually just draw a description of the problem. That would probably be best. Because if people aren't familiar with like game development stuff, then this might be somewhat foreign. So our problem is we have some world, some 2D world, and we have a big block of like bricks or something. And we just have like, say this is like 100 by 100 grid of individual components that are sort of glued together. And just ignore the fact that obviously that should be made more efficient by making them all one thing. So we have 10,000 things that are arranged in a square, and then we have our player. And these are bricks, so we don't want our player to be able to pass through them. But how do we do that? Well, there are 2 components to any sort of algorithm like this. They're called the broad and narrow phases. So the narrow phase is when you get down to like individual things. So for each brick square, we will check that against our player and do some math to make sure the collision doesn't happen or resolve the collision if it already has happened. The broad phase is going through all of those bricks and seeing which ones even need to be checked against our player. Because if we have 10,000 bricks and 1 player, that's 10,000 checks per frame. If we have a player and, I don't know, 5 enemies on the screen, that's 60,000 checks per frame. It's just not going to work. And so that's what we're focusing on. The narrow phase, obviously, that's very important because if your math to resolve the collisions doesn't work, then there's just no point. But that's more of a mathy linear algebra physics problem than it is an algorithmic problem. So we're going to be focusing on the broad phase, which again is just some algorithm that goes through everything in our world and figures out what needs to be checked so that we do the minimum amount of work. For example, in this case, if our player is moving like this much this frame, then that's sort of like the maximum area they can get. So we might say, well, we don't even need to check collision at all. They're not going to hit anything. If they were much closer, say here, and they were moving about that same amount, then we would only need to check them against, that whatever percentage of the total bricks that is, 1/10 or something. And this is obviously desirable because we don't have all the time in the world each frame for collision resolution. We want our game to be able to do other things at that time as well. Okay, so this is efficient global 2D collision detection and prevention. The prevention part, as I said, we're sort of going to ignore because we don't have time for that. That's the narrow phase stuff. And another thing is that in all the examples I'm giving, they're going to be non-rotating axis aligned rectangles, which means they are not rotating, but also they're not already rotated relative to each other. They're all sort of laid out in a grid. And moving at reasonable speeds, that's just sort of an inherent limitation of this. But even though all my examples are given in this, we will see that that's not actually important. I just decided to do this because it's easier to draw squares. But the way we will implement this, it sort of decouples the broad and narrow phase, such that you can have any collision detection and prevention stuff that you want for any sort of polygons. And this just deals with finding the pairs that need to be resolved. Okay, so the solution that they came up with is something called a quad tree. Now, a quad tree is, it's just a general kind of tree structure, but it's somewhat different from a binary tree. Obviously, a binary tree has 0, 1, or 2 children. A quad tree, you probably guess, has 4 children, but it's not 0, 1, 2, 3, or 4. It's 0 or 4. And so what we can use this for is recursively subdividing a 2D space. So we have our whole world is that sort of outer box. And then you can see we subdivided that 4 times into the 4 quadrants. And then the bottom left one here, we did that one more time. This one we did one more time, one more time, one more time, one more time. So it gets very divided. It's a recursive process. That's why it's a tree. And in each sort of quadrant of this, what we store are things moving around in our world that we want to not collide with each other. And then every frame, because assuming we partition everything correctly, then all we have to do is, instead of checking each element against every other one, we only check each element against those that are in its same quadrant. So in this case, every element is in a unique quadrant except C and B, so only those 2 would need to be checked. Now, this is a super extreme example because there's only 10 elements or something there. And we would never want it to be that divided for just 10 elements. But I think it does a good job of sort of illustrating the structure of it. And now here's what that tree looks like under the hood, sort of. So we have the root, and then it goes the order of the leaf nodes is top left, top right, bottom left, bottom right. So A is the only one in the top left quadrant, and then the top right quadrant is super, super subdivided here. Then we have our one node that just has multiple C and B, multiple objects in there, and then E, just like A, is alone. And the most important thing to realize from this is that each node, again, it stores 0 or 4 children. If it has 4 children, the node does not store the objects that are in it. The objects are only stored at leaf nodes. And that's just the way I chose to implement this. I'm sure there is a better way to do this, quite frankly, a more efficient way where some combination of storing them at the leaves and at each sort of non-leaf is used. But anyways, this is what we've got. So if you're curious, this is what a better representation of an actual one would look like. All I did is I took this and I removed all the ridiculously small subquadrants. And we'll look more at this and when things need to be subdivided in a minute. Okay, so let's say we have this, and for some reason, all of these things, all the red dots are static. Maybe those are our bricks. And then our player, we add a player into the world, and he moves from position to position throughout the sort of different quadrants of our graph. We need to look at what actually happens as he moves throughout the tree. Well, this happens. These sort of dashed green lines show subquadrants that temporarily exist. So my player enters the world at P0, he moves to P1, and when he moves to P1, this whole bottom quadrant subdivides. Then when he moves out of P1, that quadrant sort of re-merges. So we get just the original thing, one big rectangle with C, B, and D. And then a similar thing happens here. He just moves through P2 to P3 to P4, and then P4 subdivides. And then if he was to move out of P4, like this would be the end result of the tree if my player traced out the path from P0 all the way to P. Okay. So how did I choose, like how did I decide, or how did I know that these things would subdivide? Well, that is a parameter actually that we can tweak, which is a good thing about this implementation. I think it's sort of, you can tweak it to best fit your use case. And you know, the number of nodes, the number of child nodes is not something that can be tweaked. That stays at either 0 or 4, but the maximum number of elements that a leaf node can contain is tweakable. And in this case, even though it's like a super small number and it's probably very inefficient, just for the sake of illustration, I chose that value to be 3. So I call that the threshold value, is the maximum number of elements that can be contained by a single node. So we see here that this bottom left one, it already has 3. It has C, B, and D. And then when the player moves in, that's 4. So we have more than the threshold, which signals to that node that it needs to divide. And now I think I will give you sort of an expansion on that illustration, a somewhat different case. So I'll just zoom in on that bottom left quadrant. We have C, B, D, and let's say we have some other points in here. So this is already like subdivided like that. And then what we do is, ooh, how do I want to show this actually? Essentially what I'm trying to say, I can't think of how to draw it right now, but this division needs to happen recursively, because we can end up in a situation where when we say like this, here's the best way to draw it actually. I'll take just a different example, not the one on the slides. So let's say we have these nodes here. And there's only 3, so this isn't subdivided yet. But then our player comes in and goes there. So we subdivide this, but they're all still in one quadrant. 4 is still greater than the threshold value of 3, so we need to recursively do it and subdivide once more. And in this case, we just need one more subdivision, and that fixes our problem. But that needs to happen essentially to infinity, but we'll talk about like the actual practical lower bound on subdivision in a minute, which is a very like important and key part of our algorithm actually. Probably not in a minute, probably towards the end actually. Okay, so all of that is good. Hopefully I did a good job of like, I haven't really explained anything yet. I've just showed you what we're trying to do. We have this tree structure that recursively subdivides itself as things move throughout the tree. And then it also sort of recursively remerges itself. Now, the reason for that remerging is actually probably a question that you have, which is if our goal is to, if like the problem we're trying to solve is dividing our world such that the minimum number of pairs of objects need to be checked, then surely we want it as divided as possible, right? Because that means we'll perform the minimum number of checks every frame. And that's a good intuition, but it sort of assumes that other than the actual collision checking, our tree takes no time to process anything, which of course is not true. And in fact, as you get smaller and smaller subdivisions, in the particular case that we're looking at, where we're not dealing with point masses, which I'm about to talk about, we're dealing with rectangles that have area. If you have a super subdivided tree, then a rectangle has to be contained in all of the small little tiny quadrants that it intersects. And that actually adds a significant amount of overhead towards just moving in and out of all those tiny quadrants. So we sort of have this optimization problem where we have like an upper and lower bound where we want our tree to be as subdivided as possible so that we do as few checks as possible each frame, such that no quadrant like contains more than the threshold value. So we'll subdivide until we hit that threshold. And that's why it's important that we can tweak that threshold, because depending on how your game works, depending on how things move around in the world, or how big your tree is, maybe that would affect it. You can tweak that threshold value, which overall will just determine how many times your tree subdivides, and stuff like that. And that's actually not something that I would expect to affect performance in like different types of games necessarily. But it is something that would be useful no matter what, just when you're designing a game, because I mean, how are you supposed to like deterministically figure out the best number, the best threshold value if you can't just run tests on it, basically. Okay, so now that we've looked at that, let's look at the actual problem that we're solving, which is rectangles. So I have 3 rectangles here, and we need to look at what happens when I insert a fourth. Again, this is assuming the threshold value is 3. So when I insert one more, this whole thing needs to divide. Now, we could do this so that as sort of an approximation of the simpler examples I just gave using points, where the midpoint of each rectangle determines which quadrant it's in, But that leads to problems in the narrow phase, where say I have like A is up here, B is over here, and both C and D are in this quadrant because their midpoints are in this quadrant. Well, if A is moving fast enough to the bottom right that it will actually intersect with D on this frame, it's just going to pass right through it because D is in the bottom right quadrant, A is in the top left quadrant, and even though there is potential for intersection based on A's velocity, it won't be checked against D because D is not in the same group. So what we need to do is insert every rectangle, every rectangular sort of element in our world needs to be contained by all nodes that it intersects. So in this case, A and B would be, in the top left and top right separately. C would be in both of the bottom ones, and D would be in all 4. So this is sort of what that would look like, where you can see that every element will be checked against D, which is the correct behavior there. So let's just add some more nodes. So we add E, and now E is a part of both of the right ones, so the top right and the bottom right. And if we add F, well, we now have to divide, even though this looks a bit weird because it doesn't quite seem that we have 4 elements in either of these right-hand quadrants, but because we're doing it just based on any intersection of a rectangle, then we have BDFE in the top right and DFEC in the bottom right. And so you can see here, we sort of recursively divide that. I won't go through that. I've showed these examples enough. Yes?
So that would solve the problem with the rectangles and make it any shape using that?
Yes, exactly. That's a good point, and I should bring that up actually. So I've said that I've just been saying that we check for rectangular intersection against a quadrant. Well, if you think about it, what that boils down to is just a square, basically a quadrant versus a rectangle, which is very simple. But we could, and we'll see this in the way that we design things, we could implement it so that these shapes could be anything. They don't even have to be the same shape. It could just be a generic sort of polygon class. And in fact, let me draw this because this is pretty important. So I could have like different objects of different shapes. They don't have to be convex or anything. You can, as long as you can write a collision detection algorithm for them, then you can insert them into this tree. So I might have a triangle there. I might have sort of a rotated square there. And for each of these, we just assume that there's a correctly implemented test that tells you whether or not they intersect a rectangle. And if they do, we would insert it into that tree. So let me give these some names and we can draw the tree out. A, B, and C. So we have the root. And then in the top left, we have A and B. Top right, we have just B. Then we have all 3 in the bottom left. And in the bottom right, we have B and C. So yes, these could be anything. It's just that, again, for the sake of example, it's a lot simpler to show rectangles. Okay, so let's sort of look at now the two classes that we're going to use to represent this. And this is sort of maybe a point where this gets weird because, you know, when you see a tree, sort of any sort of tree data structure, usually that's just one type. It's just like a tree node type. And then those are, you know, linked together with pointers or all shoved in an array or something like that. But there's another thing we want to solve, which is sort of, I guess, exemplified by this, which is say that we don't have a general polygon class. Say that objects A, B, and C are all of different types. So A is like rect, C is a triangle, and then this is, I don't know, something weird. We want our quad tree to be able to contain all of those. And all of them, even though they're different types and have different, you know, collision properties and stuff like that, we need to be able to handle them, and we need some sort of unified interface for our tree to interact with so that it knows that it can check if something intersects a quadrant, it can insert it into that quadrant, it can check for, or it can actually resolve the collisions in a generic way, regardless of what the actual objects themselves are. And so we're going to end up with two classes. We're going to have a node, which is the actual tree, the thing that builds up the tree structure. And those nodes will contain our second class, which I've just called element. An element is basically a wrapper class. It's sort of a proxy for anything you want to put in there that, you know, belongs in the world. In this case seems sort of crazy because, like, why would you ever have a shape like that? But this is actually useful even in the very simplest case, like this brick one I gave at the beginning. Because, for example, like our player is moving around, right? But our bricks aren't. Our bricks are just sort of static map geometry. And so those are certainly different classes, and we may not even necessarily have like a class representation of a brick or something, whereas we certainly would for a player. Our bricks would sort of be like just like baked into the map data is what I'm talking about. And so in that case, we actually need this sort of proxy idea where we have our player, which is wrapped in an element that has this generic interface that the quad tree can interact with. And we have our bricks, which don't have any other representation than just their hitbox, which is just an element in the tree that is at the given position and the given dimensions of those bricks that don't move around. Okay, so let's look at the node class. We'll look at sort of what it contains. So it has 4 child nodes, 0 or 4. It also stores its parent node, which is uncommon for a tree. But the reason we're doing that is to support the merging operation. Because if we have 4 elements in a quadrant, one of those moves out. If we have 4 elements in a quadrant, then that quadrant will be subdivided. If that element then moves out, then there are only 3 in that bigger quadrant, that original one. So we remerge all the parents. So what that'll look like is, say I have this, actually, I'll draw the initial. So say I have this initially, and then my player comes in and messes everything up. This is my player, and then my player leaves. So what we want to go back to is this, because that's sort of the constraint model we're working with, is everything needs to be as subdivided as possible up to the point that the threshold number of elements are contained in a node. So when our player leaves, we see, okay, so, well, initially, I guess what this would look like is this, right, where it's still subdivided, but our player is gone. So we would take this sort of outer one and look at all of its subdivisions and sum up the total number of elements contained in all those subdivisions. And if it's less than the threshold number, then we know that we can safely merge it back into one thing. And we'll actually look at like the algorithm for merging in a minute. It's just that's why the parent node is there, when usually in a tree you would never have that. Each node also needs to store its position, because, you know, a node represents some partition of our world's space, some area. And so it needs to know where it is. And I've just assigned it to the bottom left corner. This is sort of assuming like your basic graph axis layout, where positive Y is up the screen and positive X is to the right. So having things at the bottom left corner is just a good standard for that. Each node also needs a single dimension value. And this is because they're squares. They're not rectangles. And that's actually necessary. And we'll see that near the end of this related to that thing I was talking about like the practical limit of subdivision. It's related to these things having to be squares. And when you have position and dimension, then you can check for intersection against things that you might contain. They also obviously store a list of elements. And again, the sort of list of children, the 4 child nodes, and the list of elements, those are mutually exclusive. You can't have both. You have one or the other. Okay, so let's look at the element class, what that contains, and then we'll get into some of the methods of each class. So of course, an element contains a position, and it contains a dimension vector. They don't have to be squares, but for this example, I'm assuming they are all rectangles. So it'll have an X and Y position and an X and Y dimension. They also have velocity because we assume that they're moving throughout the world. If they are static, like our brick example, then the velocity would just be 0. But we still need that sort of in our generic interface because we have to assume that for any given thing, it can be moving. And there would just be I don't think any real performance gains if you had 2 separate classes, one for static things and one for dynamic things. I don't think that would matter. And here's probably the weirdest part, is that each element also has a list of nodes in the tree that it is contained by. So this is something that we touched on a bit, I think, when we talked about linked lists, so I'll draw that example out and then I'll show you how it relates to the tree. So say we have this list, and actually say it's just like 1,000,000 elements long. And all we have is a pointer to the head. And if we want to get something that's in here, at like index I equals 10,000, then we have to start at the head and traverse from node to node 10,000 times till we reach that thing. But if instead what we do is for a given data element that our node contains, well, I don't know why I drew a star. Let me give this a name. I'll call it D. Then D is some structure. It has some stuff, but it also has a pointer to the node that contains it. And in some specific cases, this is actually very useful. It's not useful if you are only storing, if the only place D is stored is in this list, because then if you want to get the node pointer that D stores to itself, you have to first find D, which obviously that's just useless. But in this case, we'll see that our elements are stored sort of externally of our tree as well, and our tree just contains pointers to them. And what that means is if we have an element and we have a list of the nodes that contain that element, then we can go straight to all the places where the node is in the tree, which is great. Because, and sort of, I think that's very interesting actually, because when you see tree algorithms, usually it's like, okay, everything is log in. That's just how it is. That's what a tree does. It sort of recursively subdivides things. So that's a logarithmic time. And in this case, sort of insertion and removal are log in, but actually getting somewhere, which is the most frequent operation, and I'll explain why in just a second, that's constant time, because we already have a list of the things that we are checking against. Okay, so I guess before I jump back into the slide, why is getting somewhere the most common operation? Hopefully that's actually a very confusing statement, because the point of what we're doing is creating something that sort of dynamically changes its shape to match the objects in our world. As things move around in the world, it reshapes itself. And so surely reshaping should be the most common operation. But actually no, because if you consider the speed that games run at, it's like at least 60 FPS. For like high performance games, usually the cap is 300 or 400 FPS. And so the amount that the amount of distance that objects cover in a single frame is like actually nothing. It's so tiny, unless they're moving insanely quickly, in which case this whole thing just breaks down anyways. But because of that, what we're doing, like every frame, is checking for collision against the objects in the same quadrants. And the time when we need to reshape our tree only occurs in the very rare instances, the one in thousands of frames where something is actually crossing the border of existing quadrants. And that's when we need to reshape. So having, log in time to reshape the tree is not great. But if you consider that it's happening almost never compared to just the regular access time, which we will make order one, then it's fine. It's totally fine. Yes.
So when you say reshape,
Mhm. That's what I mean. Yes, subdividing and sort of remerging if stuff moves out. Yeah, that's what. Mhm. So it depends. The question was, if one node moves to another quadrant, would you have to reshape them? So it depends on what's already in those quadrants. So let's say I have this example where I have my player here and I have three things there, and then my player moves one quadrant to the right. Well, this one on the left has to merge, and this one on the right now has to subdivide. So it is reshaped because all of these other things are distinct. Mhm. Yes. Oh, I see what you're saying. So if my player was just moving from here to here. Yes. You do. Yeah. And that's essentially just exactly. It's not nearly as expensive as merging and dividing, because all that's doing is taking like the pointer that this node has to this element and removing it from that node and moving the pointer into this node, which is pretty easy. Okay. So that's why elements know where they are in the tree. And that pattern actually is super useful everywhere. That I think it's called an invasive or an intrusive pattern. Usually you see it with linked lists, but here you can also see it with a tree. Of just having something where usually the time to get an element is greater than constant. You just can sort of cheat that and just using more space, store a pointer to where it is and get there immediately. That's useful in many different places. Okay, so elements also contain, so this list of nodes is essentially the parents of that element. That's the terminology of using. A parent is a node that contains an element. An element also contains a set of nodes, not a list, a set of nodes that are the parents of the nodes in this list. So those I will probably be calling grandparents. So let's look at what that means and why it needs to be a set. So for this example, I'll have to draw stuff as rectangles. So let's say I have my player here, and it's contained by this quadrant. It's contained by all four quadrants. So that's its sort of parents list. I'll call these quadrants A, B, C, and D. Okay, its grandparents list is all, it's the sort of all-encompassing one of all of its parents. So that would just be, I guess I'll call that E. So it just has one in this case, and this is a set. So why does it have to be a set? Well, consider the case where, and I'm not drawing all the other nodes here, just assume that it needs to be subdivided this way. Consider the case of this, where like multiple nodes that are the parents of an element have the same parent. So a node can have like the same grandparent more than once if we just keep a list, which is not like, it's not harmful, but it's just, there's no reason to do that. It's just extra processing to see if we've already checked a grandparent. So instead of making this like a list containing E, conf E, we just make it a set containing E. And when we try to add E more times, it just nothing happens. Okay. Oh, and the reason we need grandparents in the first place is for merging. Because when we know where parents are, that's good because we need to be able to go there and see all the elements that are also in that parent to check ourselves against them. But if we move out of a node and that node now needs to be re-merged, that merging operation has to happen on the grandparent. It can't happen on the parent. And so that's the main reason that each node actually stores a pointer to its parent, is so that we can populate this grandparents list for the element. And this is just sort of a recap of what I said before, which is an element is just a wrapper class for things that exist in our world, whether they are dynamics like the player or enemies that actually move around, or just static geometry that is just sort of, you know, baked into our map. We still need some representation of those, and this provides a convenient way to do both. Okay, so I'm going to try to get through most of the methods that these things have, most of the big ones, and talk about sort of how they work. So I've already talked about adding. That's just like inserting into a node, and that will trigger subdivision if necessary. Deleting is just the opposite. Dividing is that recursive subdivision. Merging is the opposite of dividing, where if I have a node that has 4 children and the total number of elements in those 4 children is less than the threshold value, then I re-merge them and I bring all of those elements up to me and delete my children because I no longer need them. And that has sort of a helper method, get unique elements. And an element has quite a few more methods actually, which again is sort of a weird thing because we usually would think, okay, the tree is doing all the management stuff, but these things are interconnected quite strongly. So they have this move method, which is responsible just for actually moving, for updating their position and dimension and velocity and all of that for the current frame. Then update is where all of the narrow phase stuff happens, which again, we're not going to talk. We're not going to talk about the specifics of resolving collisions. Just know, we're just going to see that they do happen. So basically what we do is we go through a list, we go through the list of our parents. For each of those parents, go through all the elements in each parent and compare ourselves against each other. Then we have just a method for checking if it intersects a given quadrant, so we know that it needs to belong in there. We have the resolve collision, which is sort of a generic virtual method that will be implemented by a child class of element that tells it the specifics of the geometry of what it contains and how to handle that. And then is contained by is sort of the, oh, sorry, I said intersects was the one for checking if something is contained by a node. Intersects is checking if it intersects a different element. Is contained by is if it's contained by a node. And for rectangles, those happen to basically be the same algorithm because a subdivision of the quad tree is just a rectangle and every other element is just a rectangle. But again, we want to write this in a generic way so that we have this broad phase algorithm and we can just plug in whatever narrow phase specific operations we need for whatever crazy geometry we have. And then there's some helper methods basically. And then of course a delete operation, which just removes it from the tree entirely, gets rid of it. Okay, so let's go through the basic like overview of the algorithm for all these big methods. And the next time, I think I will be able to get through all these today. So next time I will have the code up and ready. Again, I won't have time to write it, but I'll have the code that I can show to you and sort of show you how it maps to this. And then maybe I can show you the effects, like actually running this and how it compares to the original problem we had of like checking our player against 10,000 rectangles in the frame. Okay, so the Node.add method, it's recursive. This is a tree. And so when we add an element to the tree, all we have is a pointer to that tree's root. So add is always going to be called on the root. So if our element is not contained by this node, then we just return. And if our element is not contained by this node and this node is the root, we have a problem, because what that means is whatever element we're trying to insert is sort of outside of the area of the world that this entire tree controls. So I guess I could draw that. If I have this huge thing and it's subdivided in all these different ways, stuff like that, and I try to insert my player, that's a massive player. Let's say my player is really tiny, like there, and I try to insert my player into this sort of outer one. This is the root, this big outside box. Then that's an error, because my tree can't, get bigger past the root. The root is supposed to encompass the whole thing. So this probably means that you spawned yourself in an incorrect location, or there's some other bug somewhere in your game code. So we need to just error that. Otherwise, it's not a problem. Because this happens recursively, it's very likely that most of the nodes in the tree won't actually contain something. So we just return and it's no problem. Okay, the next part is where the subdivision happens. If the current node, which at this point is guaranteed to contain the element that we're adding, because we did that check and we return if it's not true. If the current node contains the threshold number of elements, well, we're adding a new one, which means that we need to preemptively divide. We divide before we add. And that's just a decision I made. It's essentially the same thing as saying, well, can I have up to my threshold value -1 elements, or can I have up to my threshold value inclusive? And that's just an implementation thing. It doesn't really matter. I just decided to put the divide check here. Now, once, so that's an if statement. If our current number of elements equals threshold, then we divide. After we do that, if the node is divided, which could have just happened, then we add our element recursively to all of our children. And that is essentially what that says is like the most basic description of the node I gave at the very start, where a node either has 4 child nodes or a list of elements. We can see that in this case, if a node is divided, meaning that it has 4 child nodes, then we add the current element we're trying to add to all of those children. We don't add it to ourselves, because we have children, we can't have elements, but our children, they might be able to have elements, or their children's children, and so on. So that's sort of the recursive call. And then finally, we have sort of a second base case, where the first one is if the element is not contained by the node. The second base case, base just meaning it doesn't recurse. So if our node is not divided, meaning we have less than the threshold number of elements already, then we just add our element to this current node. So in other words, this is saying if we're at a leaf node and that leaf node contains the element we're interested in, we add it. Okay. Delete element is a bit different, and most of the work actually happens in the element class. So we'll look at that. Now let's look at the divide, which is like one of the big operations. So the big operations are adding, removing, which we'll look at in a second, dividing and merging. So dividing is also recursive, of course, as I showed you. You can end up in a situation where if you have like, where was it? If you have this arrangement of things, then there's still 4 elements in that top left quadrant. So we need to divide again and again and again and again until it's resolved. But here we'll see the practical limit on that subdivision. So if our node's size is less than the minimum size, the minimum size is something that we will set that's sort of external to the tree. It talks about properties of objects in our world. Then it's an error. So that minimum size is, well, there's sort of 2. One of them is the minimum size of an object in our world, which in this case I've assumed is basically 1 pixel, because this is a 2D game, so size always maps exactly to number of pixels because there's no sort of scaling or zooming or rotation. So that's the minimum size of objects, which I think is fair enough, because if you have an object smaller than a pixel, like what are you even doing anyways? It doesn't make sense. Now, the minimum size for a node is slightly different in that it should be at least as big as it needs to be to contain the threshold number of single pixel elements. So in this case, where our threshold value is like 3, well, the smallest node size that can contain 3 single pixels is a 2 by 2, because that's 4 total pixels, so 3 fit into that. And if our threshold value was like 8 or something instead, then the minimum size of our node should be a 3 by 3, because that's 9, and so it can contain 8 of the single pixel. So unfortunately, even though that like smallest case will never really happen, basically, you still have to account for it because it is a recursive process. And at some point you have to stop recursing, which let me explain why actually. Like, when would this happen? Well, there's 2 cases. Did my OneNote freeze? Huh. So there's 2 cases where this can happen. One is if I actually end up in that situation somehow, just by, bad luck, basically, where I have those tiny, tiny elements. So this is 2 pixels by 2 pixels, and I have all 3 of them in there. That's one area where this will happen, because if I add a 4th one, remember that my threshold value is 3, so now this tries to subdivide. Well, in this case, actually, a threshold value of 3 doesn't make sense. Let's say, forget everything I've talked about so far with the threshold value being 3, it's now 4. So I have 4 single pixel objects already in this node, and this is the smallest node we can contain. Well, what happens if I'm in a situation where I try to add another one? Well, that means that something somewhere else went wrong. Because what that would look like is if this is the smallest object and I'm trying to insert another object, it must be intersecting at least one of these. There's nowhere within this node that could contain another object that doesn't intersect these. Either it intersects on the corner or sort of like in the middle of 2 or in the middle of all 4. There's some sort of intersection. And our quad tree does not handle these types of intersections. It assumes that when the game starts, when the world begins, there are no intersections happening. That's not like an unsolvable problem. That's just a different system that would have to solve that. Our quad tree is meant for assuming everything starts in a valid state, keeping it in that valid state. And so if something starts in an invalid state, i.e. there are already existing intersections, then we throw an error because it's not something we can handle, and it's basically just not our problem. So that's why we return if we're less than the min size. And I think I should sort of take this example just a bit further and clarify that this doesn't only happen in this case, where you have the smallest 2 things. It can also happen where I have very big things, but maybe those big things are, let's say I have like this, and these are big, I don't know, maybe these are 100 pixel squares or something. And I'm trying to insert something that is like right there. So it like just intersects like the corner of all 3 of these. Well, that's an error, because if I'm inserting something that's already intersecting, we can't handle that. And of course, if you zoom in, actually, I suppose I should have drawn this arrow the other way, because if you zoom in on that little area, this is what's happening. Even though our objects aren't 1 pixel by 1 pixel, they're 100 by 100, at like the very corner, this is the case that you get. And that's where the issue is. That's why we need a minimum size on the subdivision of our nodes. And as we'll see next time when we actually look at the code, that enforces some other restrictions on the shape of our quad tree overall, the size of that, of like each square. Okay, so that was sort of complicated, but it's a necessary step, because if we don't have that, then we'll just end up in invalid states all the time and not know why. Okay, so if that check passes, so the node is of a valid dimension, basically, then we remove all elements from this node. This goes back to, if I have children, I have no elements. So we are at the step now where I have elements, but I am creating my own children. So I need to get rid of my elements. Then I create the 4 children, and for each child, I add each element that I just contained to each of those children. And each one probably doesn't contain all of them, but we still need to check. This is sort of the same thing as this right here, this third line here. If a node is divided, we try to add it to all of my children because the check for whether or not a node contains an element happens at the top of the recursion. We don't check before we try to add, we check after we try to add. And that's just a like style thing. That's just how I tend to write recursion because I think it makes the recursive statements themselves much simpler and easier to read. But you could just as easily, like at this step, instead of just blindly adding each, you could say, if the current child contains this node, then recursively add. The same result. And then finally, we would delete all of this node's elements. So what's the difference between these two lines here? Remove all elements and delete this node's elements. Well, remove all elements, that refers to going to each element, the list of parent nodes that that element has, and removing the current node from that list. That's what that means. Deleting this node's elements means once I have created my children and populated them with all the elements I contain, I no longer contain any elements. That's what that is. It's getting rid of this node's storage of those elements because it's now been pushed onto the children and we don't want duplicates. Delete the children? I'm not sure. So we don't delete the node. We just delete the node's storage of the elements. So let me draw this out actually, because it is rather confusing. And this brings up a good question actually about ownership in this whole thing, which is a very, like if you do stuff in like JavaScript, Python, it's just not something you ever have to worry about. But in C++, it's extremely important for writing good code because you have to handle all the dynamic allocation and deleting from the heap and that on your own. And so the question basically is, if I add an element to a node, does that node own this element? Meaning that when I delete this node, it also deletes the element. It's now responsible for that element in its entirety, all the memory it takes. And the answer is no, because our elements exist independently of this tree, that they're just in the world, but our tree is sort of a partitioning on the world. But let me sort of tell you, or let me show what that means. So let's say I have just a list of my, I'll actually give the type. So I have like a vector of element pointers, which are my children. And then I have a vector of node, oh, sorry, that is not what I meant. This is the children. These are my child nodes. This, I'll just call elements. Okay, so what this division step does here is first, it goes through this list of elements. So for E in elements, and then it says like E dot parents dot remove this, or something like that, where parents is some sort of structure that stores a list of pointers to the nodes that contain it. This is a pointer to a node that contains it. So we just remove this node as a parent. Then this is, so that's sort of line 2 here. And then we create our children, we add our elements to the children. And then after we've done all that, so there's some extra stuff in there. After we've done all that, we actually just get rid of this. We basically would do, if this is a vector, which it kind of shouldn't be, but that's an implementation detail, we do children.clear. Because that, sorry, I keep messing that up, not children. That would lead to exactly the problem you are asking about. We would do elements.clear because we now have children, which meaning that we don't store elements. So this vector containing our elements is just wasted space because we're never going to use it anyways. So that's what elements.clear is. Good question. Okay, so then we have merge. This is the last big one. And then we have some stuff from element, which we'll have to finish next time. But let's look at merge. So if our node is not divided, meaning, and we can check that just by seeing if we have any children. If we don't have any children, then we just return because there's nothing to merge. We're already The next thing we do is sort of weird. It's an operation that returns a set of elements in all of my children recursively. So if I'm this node and I have these children with those elements in those children, and actually I should draw these as rectangles because that's the whole idea behind them being a set. Okay, so get unique elements. I'll just abbreviate that. Will return a set containing A, B, C, D, E, and F. And it builds that up by visiting each of its child nodes recursively. So if this child node happened to have children, it would continue the recursion and just adding those elements to the set. And this works super fast. It's super easy because those elements are really just pointers, and a pointer is just a number, and you can check if a number is in a hash set in constant time. That's super true. And so the reason it's a set, though, is that you can see that some of my children contain the same node, like this one and this one. Those both contain the element B, because B is big enough to fit into both because we're dealing with rectangles and not just points. And in the same way, F fits into all of them. So that's why it's a set. And we're not actually interested in the elements themselves. We're only interested in the number of them. Because if we visit all of our children recursively and we have less than the threshold value of elements, then we know we can merge. Because what that means is I have 4 children. There's a total of 3 elements in all of those 4 children. Well, I can just put those 3 elements on myself and delete my children. That's sort of the min-maxing thing we're doing. So we do sort of the reverse check here, which if we have more elements than we can fit in a node, then we just return. Otherwise, we go through each element, which again, we don't care what those elements are in particular. We've already done all the processing to know if this node contains them, essentially. Because if they exist in a child node, then they're guaranteed to exist in a parent node, because parents are always bigger. So if they do, then we erase this node, the node that we're in, from that element's grandparents list, because this node was in one of our children, which means that its parents contained that child, and so its grandparent contained us. Then we basically just clear all of that elements, all of our children from that element's parents list, and then delete all of our children, and for each element, add it back to ourselves. So that's sort of, it's literally just the reverse operation of a divide, where divide is for each element I contain, tell that element that I no longer contain it, create 4 children. For each of those children, add every element, and then delete my local copy of the elements. This is just the opposite, where for each element, erase myself from the grandparents list and the child that it's in from its parents list, delete all of my children, and then create my elements. So divide is delete elements, create children. This is delete children, create elements. And I believe that, yes, that brings us to the element class. So there are several important methods here. As I said, these things are very interconnected. And so a lot of the actual functionality of this whole system lies in the individual elements themselves. So we will have to take some time next time to look at that. But yeah, I think we're on track. Next time I will certainly have code prepared, and I'll have a little demo and stuff that we can see at the end, just to make all of this concrete. But that's all we have time for today. Are there any sort of remaining questions about anything? No? Awesome. All right. Well, I will see you guys on December 2nd, so in 2 weeks after the break.